All right. Now we're going to conclude our discussion of electrostatics quantities with our fourth and final one, the electric potential. So, after we looked at force, which was a vector interaction between two charges, we looked at this concept of a force per unit charge, also known as a field, which gave us a vector at every point in space representing the direction of force on a small test charge. Similarly, we're now going to define an energy per unit charge, which is the electric potential. And this is the same electric potential that we looked at with circuits. So the difference is because energy is a scalar quantity, that means this electric potential will also be a scalar. So instead of assigning a vector to each point in space, which we looked at sort of a wind map, the electric potential just assigns a number to every point in space. And the most common thing we've seen with this is either a temperature map, or what we're going to find useful is actually thinking of this as a height map. So we have this diagram called an equipotential diagram on the left, which gives heights at each point, where the height is actually visualizing this electric potential. So you can see where the positive charge is located, there's positive heights or hills, and near the negative charge, there's valleys. We also like to visualize this in 3 dimensions sometimes because it's a lot more visual that way. So the same plot in 3D is shown on the right, where you can see that this positive charge makes a hill or a positive spike, and the negative charge makes a valley or a negative spike. So thinking about electric potential geographically actually makes a lot of sense and will help us solve some problems, especially when we relate this to the electric field. There's a nice visualization in terms of the slope of the terrain. So to begin, you probably could have guessed that this would be the definition of electric potential. Just like electric potential energy looked like Coulomb's law, except with an R instead of an R squared, electric potential looks like field, except with an R instead of an R squared. Because each individual charge can generate a hill or a valley, so we just have one charge involved. And since it's an energy-related quantity, it has the R and not the R squared. So just like with electric potential energy, just to make our height map make a lot more sense, we define the zero height location to be very far away. That way, your sea level is set to be flat far away, so any changes to that are caused by charges. Additionally, it's the same principle as before, where if you're trying to find the total height at a location, you can just add all of the height contributions from each individual point charge. So let's of course verify this formula for electric potential using our definition. So by definition, we said that the electric potential energy between two charges was kQq divided by R. Then, by definition of the electric potential V is defined as the energy per unit charge. So this is the same thing as just saying take our expression for UE and divide out a test charge. So we take our kQq over R and divide out one of the charges, and we see that we get that cancellation as expected. So we get V is just equal to kq over R for a single point charge. And this is a scalar, so this makes all of our math quite simple. So for an illustrative example, we pick this example of 12 charges spaced around a clock. So each of these charges are equally spaced around a circle, and we have 12 of them. So we're going to consider this point at the center of the circle, and we're going to be interested in finding the net electric field and the net electric potential. So first, going back to electric field, well, each of these point charges is going to be generating a source at that point, because again, positives are sources. So maybe if I consider this charge in blue right here, that would generate a field pointing directly away, so to the left. But then if I highlight this charge in green, Directly opposite it on the clock, we see it generates a field exactly canceling. And we can do this with any pair of charges on the clock. So maybe instead let's pick one of them at the angle. So maybe I pick this charge in purple up here. That's of course going to act as a source and push away. Maybe I can do better trying to make it the same length. And then maybe I'll pick one final charge in orange here opposite it and see that this also generates its own source opposite. And those also cancel. And we can repeat this process. We can keep on going. And every pair of charges, the sources are going to be competing and they perfectly cancel. So due to symmetry, there's our word again. Due to symmetry, we can see that there will be no net electric field at the center of the clock. Because these pairs of charges on opposite sides are just generating equal but opposite fields. But now we get to something different. We get to potential, which is a scalar. So if we think about this as a height map, it shouldn't be zero, because if you think of this as like a piece of fabric, each of these plus Q's is going to be generating a little spike. So if I have 12 positive spikes around this circle, well, all of these are going to be pushing the terrain up. So I definitely don't expect zero here. And we're not going to get zero, because just by definition, the net electric potential is just the sum of all the little potentials, KQ over R. And we can use symmetry again here, but we don't have to deal with anything with vectors. We just use, well, there are 12 charges, and each of them are contributing KQ divided by big R, where R is the radius of the circle. So this is just 12 KQ over R, which makes sense, because this is just telling us our height at the center is just 12 times the contribution from one of the charges. Now, the real power of electric potential is seeing what happens when there's not symmetry, where the electric field would be hard to calculate in comparison. So we're going to answer the same question, basically discussing the electric field and electric potential at the center, but this time we have removed the 1 o'clock position. So in this case, we see that a lot of the charges still do cancel if we're looking for the electric field, because we have these opposite charges, we have these opposite charges, we have these opposite charges, and so on. But due to the broken symmetry, we see that this lone charge down here at 7 o'clock doesn't have its friend at 1 o'clock to exactly generate a countering electric field. So we are going to get a net electric field, KQ over R squared, towards the 1 o'clock position. But when we say describe why it's no longer simple to calculate the E field at the center of the circle, remember, if we say find the electric field, we don't just mean the magnitude, we mean the direction. And this is not an easy direction to determine. You can practice your unit circle skills or do some clever division by 360 to figure this out if we really wanted the direction. But the whole point of this problem, this first part at least, is this would take a lot of work to figure out in unit vector notation what this electric field is. So by breaking the symmetry, this problem just became a whole lot harder because electric field is a vector. But why is this not an issue to find the electric potential at the center still? Well, electric potential is a scalar. So if originally I had 12 KQ over R because I had 12 spikes adding to the height of my terrain, well, I just removed one of the 12 spikes. And since everything happening here is equal, we just can use symmetry again and use the fact that electric potential is a scalar. So V net, it's still the sum of all the KQ over R's, except now I just have 11 of them instead of 12. So, no issue here. All right, now we're going to do a ranking task here. So we have a positive and negative charge, and we're looking at the electric potential at different spaces between these charges. So, first of all, we know that electric potential is a scalar. So I'm just looking at how these heights are going to add directly. So we know that this negative charge represents a big infinite negative spike or a valley, and this positive charge represents an infinite positive spike or a hill. We also know that due to symmetry, directly in the midpoint of these two charges, the terrain is getting pulled equally up and down, so we do know that potential would be equal to 0 in the center point. So we know that anything to the right of that is going to be a positive potential, anything to the left is going to be negative. So the real trick with this is, how do we compare the negative potential values and the positives? Well, also realize that potential is a scalar. So if we're trying to see what potential is the most negative, we're just saying what is closest to the negative spike and furthest from the positive spike. So this does actually mean that A is the most negative of the potentials because I am closest to the negative spike while still being farthest from the positive. And then by a similar argument, D would be the most positive because D is closest to the positive charge while also being farther away from the negative. So the downward push of the terrain isn't as much. And then we're just comparing B and C. Well, B is closer to the negative than the positive is. So we know that it's actually just going to rank left to right like this. So then to justify our ranking, we're just going to quantify exactly that. Positive charge makes a positive contribution. Negative charge makes a negative contribution. Electric potential falls off with distance. So if you're trying to get the highest positive number, that would mean that you get the greatest electric potential when you're both close to the positive charge and far from the negative, which is why point D is at a higher potential than C. There is another argument we could use to try to justify this using fields, but that is for a later section. So now we'll revisit an E-field problem we did before, where we had two positive charges and we found the 0 field location between them. This time, we have two opposite charges, and we are going to be looking for the location of 0 potential between them. So first, let's just justify that a 0 potential location exists. And we know that that has to be the case for this, because if the positive charge is a positive spike or a hill, and the negative charge is a negative spike or a valley, well, if I tried to draw my potential, of course I couldn't actually draw it accurately because I would need to be able to draw infinity, but essentially we'd get something that was like this, where we'd get a hill and then an even deeper valley, something like this. So we know that somewhere between the left and right charge, you got to somehow cross between above sea level and below sea level. So where is that going to be? Well, the negative spike is bigger. So what that means is that in order for my positive charge to generate enough potential to counter that, I must be closer to the positive charge. Because the negative charge generates a larger potential at the midpoint. You could also look at the midpoint if you wanted to. I could say at the midpoint, it's going to be negative potential because I'm feeling the effect of the negative 3q more. But here's my justification. We know electric potential is positive near the plus q, negative near the negative 3q. So we have a sign change. And since the positive charge has a smaller magnitude, you need a smaller distance from this charge to generate the same potential. So I must be closer to the left positive charge, which is in the first half of the interval. So now we can find an expression for this. So we're just going to set the potential equal to 0. So we know that V from the plus Q plus V from the minus 3Q is equal to 0. And now we do that same technique we did before, where here's our charges. And we know that this x0 is located somewhere over here, which means that the remainder of our interval must be the interval d minus however much I already took up. So now this allows us to actually calculate our electric potential at each point, because kq over r for the plus q charge, well, r is just x0. And then for my negative 3q charge, it's still kq over r, except q is minus 3q, and r is d minus x0. And technically, this should be an absolute value on this d minus x0, but we don't have to worry about that right now, because this is never going to be negative. So now we just solve it. So our equation gives us kq over x0 equals 3kq over d minus x0. So we see that both the k and the q cancel. So we're just solving 1 over x0 equals 3 over d minus x0. So we can multiply both sides by d minus x0. Yeah, I think that's probably what we want to do. So we'd get d minus x0 over x0 equals 3. Cross multiplying would have done this better, I see in hindsight, but d minus x0 would be equal to 3x0. So 4x0 would be equal to d. So x0 would just be exactly 1/4 of the distance between the two charges. And actually, we could have reasoned this out a lot quicker using ratios, where if you used a ratio technique, you could have argued that since electric potential is only linearly related to distance on the denominator, you could have said that if this distance was x, to generate the same potential from a charge that's 3 times as massive, this must be 3x. So you could have just set x plus 3x equals d, and you would get the same answer. So that's not a coincidence. And remember, that technique sort of worked for electric fields. You just had to be very clever and use the fact that it would be a square root relationship with distance in there. So now let's try to graph the electric potential as a function of x. So the points that are identified are the midpoint and the interval ends. So we know that it is going to be an infinite positive spike at x equals 0, because that's where the positive is, and an infinite negative spike at x equals d, because that's where the negative charge is. We also solved this previous part and said that exactly at 1/4 d is where the sign change happens. So I know my terrain goes from positive to negative, but the actual change happens at d over 4. So now I'm just going to do my best to make a graph that accomplishes that. So this is going to be a vertical asymptote. And then maybe I get something like this. You can Desmos this and you see that this is roughly what you get. Turns out this is, I believe it's an inflection point when I looked at it. So if you actually wanted to graph it in Desmos, you could actually graph v of x equals 1 over x minus 3 over d minus x, where you just set d to be whatever you want in Desmos. And if you wanted this to work for all of space, you could actually put some absolute value bars on everything so that the distance term would always be positive. So this is actually how you'd graph this in Desmos. I always set d just to be 1, because I know it will work out if I scale everything. All right, suppose we change the rightmost charge. Describe how this will affect your graph. So let's think about what this graph how this related to the charge being negative on the right. Well, we see that the negative charge on the right is what made this graph actually dip negative and spike into the negatives. So if this charge was the same, but just was positive, then this spike would end up being positive and tend towards positive infinity. So actually, there'd be nothing pressing my terrain down at all, so I'd get a strictly positive graph with an infinite spike at plus d as well, instead of a negative spike there. Come on, where is it? There it is. Now that the graph is strictly positive, you're going to get a vertical asymptote at x equals d that's towards positive infinity. And since you're making the right charge positive, both charges are generating positive potential contributions, so you can't get negative potentials anymore. So is there going to be a location where we have zero electric potential on this interval? Well, no, because we have a strictly positive graph. So if we attempted to graph this again, we know we'd still get an infinite spike at x equals 0, and we'd also get an infinite spike at x equals d. So we'd get something like this, where we'd get an infinite spike on both ends of the region, and it's going to be strictly above the x-axis. The only place the electric potential would be 0 would be at infinity, which is just our consequence of saying that our terrain flattens out all the way away. But that wasn't what was asked. It was saying, is there a location in this midpoint area? No. So one of the reasons we define potential is because it is often much easier to solve energy problems using electric potential instead of just the actual energy. So just like we have the formula Fe equals QE to convert back into force if we know the field at a location, we can do the same thing to relate energy to potential. But since only changes in potential energy matter, we will rarely use U equals QV. Instead, we look at the deltas. Because if you know how your energy changes, that will allow us to just set up an energy conservation relationship, because any change in potential must be counteracted by an opposite change in kinetic. So this actually teaches us some things about how charges behave in relation to potential. So note that a charge will speed up if delta V, if this delta kinetic energy term is positive. So if we can somehow make this boxed term positive, that will mean a charge speeds up. So we can see that since we get this opposite change in potential equals negative Q delta V, we can see that a positive charge will accelerate towards lower potentials, because if I have a negative delta V, that makes my potential, that makes my delta V negative, which makes my kinetic change positive. So I gain speed. Negative charges actually accelerate uphill because the Q would also be negative. So you need that double negative there. So this actually tells us that electric fields point downhill, which is one of the main points of our next section. So just to really study this idea, let's look at all of these possible different changes in energy that we could experience. So we're launching either protons or electrons through regions of changing electric potential, and we want to eventually rank the speed of the particle upon reaching the rightward line. And we're going to assume they don't stop or anything like that. So they're all launched with some initial speed. So the key to this problem is realizing that if we're looking for speed, that's going to be related for delta K. Because if you go through a potential change, you're going to change your kinetic energy. So we're really looking for delta K, which is the opposite of their delta U, which is the opposite of delta U, which is Q delta V. So here's where we'll use some convenient energy units. So instead of converting to coulombs to get our answer in joules, we can actually define an energy unit called an electron volt that works in terms of volts and the elementary charge. Because we see that this expression of coulomb times volts has units of energy. It's just more convenient this way. So we can just do this for each case. So for case A, we see that our delta K would be negative of my Q would be plus E, and my change in potential would be plus 1 volt. So I would get negative 1 EV of kinetic energy change. And we can check that this works because we said positive charges like to go downhill. So if I just made this go uphill towards a higher potential, it doesn't like that, so it's going to lose potential energy, it's going to lose kinetic energy. So this particle would slow down. Case B, we can argue by symmetry this will be the exact opposite of A, right? Because A and B are just reversed. So if instead it sent my positive charge down 1 volt in potential, we see we get a negative and a negative, which makes this plus 1 EV. So this would be plus 1 EV. So this one is going to speed up. And now we can just kind of quickly work out some of the rest of these here. So for C, we have a negative charge going down 1 unit of potential. And electrons don't want to go downhill because negative charges like to go uphill. So we see this is a negative. So this electron loses some kinetic energy. Case D would be plus 1 EV because it's an electron going uphill. So that gains some kinetic energy because case D and case C are sort of opposites. Again, the potential numbers don't matter. It's just the delta. And then E, well, there's no change in potential. So the electron or the proton isn't doing anything it likes/dislikes. So this would be 0 EVs of kinetic energy change. So it neither speeds up nor slows down. And then case F, well, my electron goes uphill, which it likes, and it's doing that for 2 volts. So this actually gains 2 EVs of kinetic energy. So again, this thing we calculated is not the speed. This is the change in kinetic energy. So this is telling us how much our speed basically is changing by. So case A loses a little speed, case B gains some speed, case C loses a little speed, case D gains some speed, case E stays the same, and case F gains a lot of speed. So we can do that to create this ranking here. So first, the lowest speed particles will be anything that lost kinetic energy. And that looks like cases A and C. Cases A and C tie because they lost an EV of kinetic energy. Next actually comes case E because it's the only one that didn't gain or lose kinetic energy. Then we have cases B and D because they both gained 1 EV of kinetic energy. And then we lastly have case F, which gained 2 EVs of kinetic. So again, if we just look at our energies, we can justify this by saying you lost an EV of kinetic, you didn't change your kinetic, you gained an EV of kinetic, and you gained 2 EVs of kinetic. And here's just the work. Here's the work summarized nice and cleanly. So since kinetic energy causes an increase in speed, we're just ranking the change in kinetic. which you can find by finding the change in potential and taking the opposite of that, because if U goes up, K goes down, and vice versa. All right, last problem. A point particle has a mass m, charge q. It's at rest at one plate of a capacitor. Then we are turning on or connecting this to a battery where the potential is epsilon between the terminals, and this particle is going to get launched towards the other end of the capacitor. So this is going to get launched from one plate to the other, and we're given that this speeds up during this process, which makes sense because positives go towards lower potential. So this is the case where we don't define potential to be zero at infinity, is anytime you have a circuit, we define it to be just the lowest position you can reach, which is the negative terminal of the battery. So here, our potential is epsilon, and here our potential is 0. So we can visualize this energy problem using a bar chart. So first, when the particle is first launched, we know that it has 0 kinetic energy. But we also know that since it's attached to a positive potential, it's going to have a positive amount of potential energy. And we actually do have an expression for this. We can say that this potential energy it has is QV, or Q times epsilon. Then, when the particle slams into this negative plate, or the zeroed plate, it would have 0 potential energy, because QV is equal to 0. So that must mean by energy conservation, all of its energy must have gotten converted into kinetic. So 1/2 mv squared. And we're interested in this impact speed. So we'll show 2 ways of doing this. So the first way, which is inspired by the bar chart, would say that we just set our usual energy quantities equal at the start and end when we sum them up. So initially our potential was Q epsilon, we had 0 kinetic, and at the end we had 0 potential, and 1/2 mv squared for kinetic. So then we just solve 1/2 mv squared equals Q times epsilon, so multiply by 2. So we'd get mvf squared equals 2Q epsilon. So vf would be divide by m and take a square root. All right. Now, how we'd actually do this, because it was sort of an arbitrary decision to set potential to be 0 at the bottom plate, we could also use this from a delta approach. So we could, which is usually the best one to do with potential, because potential is all about deltas. So I could set delta K is equal to negative delta U, which is equal to negative Q delta V. So this means delta K would be equal to negative. The charge is just plus Q, so I'm actually going to write that plus Q in parentheses. And then we have to think about what our delta V is. Well, our delta V, regardless, the battery voltage is epsilon. And if the charge travels from something connected to the positive terminal to something connected to the bottom terminal, delta V, no matter how you define it, is going to be epsilon, but it's a decrease. And notice this will make sense because we get a positive number for delta K, indicating our charge sped up. So now we can just set our delta K 1/2 mvf squared minus 1/2 mv0 squared equal to Q times epsilon. We see that this term is 0 because we didn't have initial velocity. So we get the same equation as before. This 1/2 mvf squared equals Q times epsilon, which means Vf is equal to the same 2q epsilon over m, as expected. Most people will eventually do this using the delta approach instead of the bar chart approach in the future, because people can generally just see that this delta V was epsilon, but we have to be careful of sign here because you'd get a non-real answer if you forget that this is a decrease in potential. So each of these has their drawbacks. With the bar chart, it's more straightforward to set up, but you have to remember to set zero potential at your lowest point, whereas with the delta approach, it's more formulaic and less easy to mess up the actual delta, but you have to remember the sign and really think critically about whether the sign of the potential is going to change, is going to be positive or negative. Oh yeah, also notice it was a positive charge, so accelerating downhill caused it to increase in kinetic energy. All right, now just a quick ratio question to fill out the page here. So in terms of VF, derive an expression for the new impact speed in terms of each of the following, so after each of these modifications. So the voltage across the plates is doubled. So our expression for V was 2 times Q times epsilon divided by M. So again, epsilon is the plate voltage. So we're just looking at what doubling that does to V in each case. So I'm just copy pasting this so I don't have to write this a bunch of times. So here's our three changes here. We're looking at doubling voltage, doubling mass, and then tripling mass and charge. Well, for the first one, doubling the voltage across the plates. Well, that's epsilon, so that's times 2. But I times 2 under the square root. So this would be root 2 VF, because that 2 ends up being square rooted. The mass of the particle is doubled. Well, I multiply the mass by 2, so it's going to be a divide by 2, but that divide by 2 is under the square root, so that's a 1 over 2 square rooted times VF. Do not rationalize. And then what if we triple the mass and the charge? Well, the charge gets tripled, the mass gets tripled. So actually this does nothing because you get a 3 on top and a 3 on bottom, which makes 1. Square root of 1 is still 1. So this is no change. And I included this to show that actually, with most of these problems, the thing that matters isn't the charge or the mass, but it's this thing called the mass to charge ratio. So you'll see a lot of things in this class depend on the quantity m divided by q, or the inverse. Yeah, so that's electric potential.